Hello. Today we're solving number 74, search a 2D matrix. This is what the problem looks like, and let me explain what it's asking. In this problem, we're given a grid. In this grid is a list of sorted numbers left to right, top to bottom. So it'll be 1, 3, 5, 7, and then in the next row, 10, 11, 16, 20 in their example they gave, and it proceeds that way. Given this list and a target number, we're asked to find whether this target number exists in this list. So we're searching this list for this grid for this number, basically. So how do we solve this? This problem is pretty reminiscent of binary search. It's very similar. We're given a sorted set of numbers and we have to look for a target number within that. The only caveat or curveball is that we're given this list in a grid format instead of a straight list. So what I'm proposing for how to solve this is, instead of us trying to format our search or write some kind of customized algorithm to look through a grid instead of a list, why don't we just write binary search and then map this grid to a list and back, so that binary search can do its thing and we don't have to come up with a whole new algorithm. So let's see what that looks like in code. I'm not going to go over how to actually write binary search or its ins and outs, but maybe I'll make a video about it later. I'm just going to write it assuming you know how binary search works. We need to, before we actually start writing binary search, we need to find the number of elements in this grid, because that's what we're going to pretend is in a virtual list instead. So height width equals length of matrix and length of the first element of the matrix, because the length of the matrix is the height and then first element has the width. So here's where we actually start the binary search part. We need to come up with our start and end indices, which start is always 0, and the end is the number of elements minus 1, because it has to be a real index within the list, because we may end up accessing that index. While start less than or equal to end, and at each step we get the midpoint, which is the floor divided by 2 of the sum of start and end. So this is the part we're going to black box for now. We need to get the value that we're going to compare to the elements in this list to figure out whether we have this element or what to do next. For now, I'm just going to encapsulate this into a get value function where we pass in the mid index. Like I said, in this function, we're going to end up mapping to the grid and then mapping back, but let's not worry about it for now. So continuing with binary search, if the value equals the target at any point, that's great for us. We just return true to say so. If that's not the case, then we break it into greater than or less than cases. If the value is less than the target, that means that the target has to be, well, either it doesn't exist or it has to be greater than where we're currently searching. So we should assign start, we should move start up to represent, to get rid of the left section that we were searching earlier. In the case that it's not, aka value is greater than the target, then we want to get rid of the right section and move our end index to denote the left section is what we're now searching. So end equals mid minus 1. If we go through this whole loop, we never find the correct target. That means it doesn't exist, and we just return false. That's the binary search. And as promised, we need to now define the get value that handles the mapping to the matrix and back. I'm defining this inline within this function because I just don't want to deal with classes and do self dot whatever. Also, this actually does save space. That's the better reason for why I'm doing this. The input I'm going to call virtual index, meaning virtual index into the virtual list. How do we convert this? Well, let's think about a grid of length 2, and I don't know how many columns, but just say we're trying to get the third element in this list, which is the second index number. Well, the row number just corresponds to how many times we can divide the width into this number that we're trying to get. So the third element goes through 1, 2, and then should be the first element of the third row. So we should do the row equals virtual index floor divide by the width of the grid. And then the element, the number element within that row is just the virtual index modded by the width. As another example, let's say we're taking the fifth element instead of a 2-width grid, then we would go 1, 2, 3, 4, 5. Like I said, every 2, aka the width of the grid, we want to advance 1 row, and then we want to just take the mod for the actual number element within that row. So now we have the correct coordinate within this matrix. We just need to return that element. So this does the mapping and unmapping for us. And that's it. We just submit it. We see that we get a pretty decent result. As far as the runtime, it's just binary search. So the logarithm of the number of elements we're searching. So log of m times n in this case, where m is the height and n is the width of the grid. Yep, that's it for today.